Okay, so we'll get started on the seminar. This is cryptography. So this is one of the ones that we're doing every single month. So there's a few things that we have to talk about before we get started. The first one is that we're going to be at Deer Hacks. So if you are at the hackathon and you're competing or you're a mentor or a volunteer, if you're going to be at Deer Hacks, which is at Mississauga, it starts later today. We're going to be there. We're going to do some workshops there. And there are some roles that we're hiring for. So there's a finance role, there's a tech role, and then if you want like the actual details, it's on a SOP, and that's fine. And maybe we're gonna play war game. Actually, we don't know. There are some good war games this weekend, but we have to see. So for the outline, this is actually kind of dense. We are going to cover the cryptographic theory, some encodings, cryptography in terms of symmetric and asymmetric, and also some hashing and random numbers, as well as some implementations such as the public key infrastructure and digital signatures. So that's kind of what we're going to be doing today. So yeah, it seems good here. OBS is fine. Okay, so I guess we'll get started with cryptographic theory. This is what Hyde is going to talk about, I think. So it's some background knowledge about cryptography, like the philosophy behind it, and other things.
Yeah. Hello, and yeah, I guess we'll just get started with cryptographic theory. Yeah, basically, when you're doing cryptography, you have messages and keys. Message is just the actual message or the data you want to send over to another person in a secure manner, of course. And the key is an actual secret key that's used to unlock the message. And of course, you can encrypt the message, and then when the receiver gets it, they have to decrypt the message. Yeah, so the idea of encryption and decryption, we usually use the words plain text, ciphertext, encryption and decryption when we talk about these concepts. Plain text, as mentioned, is a message, the actual data we want to send. The cipher would be the actual like methodology or algorithm we use to actually get the ciphertext, which is like ideally like a really unreadable or unrecognizable just junk. And then after we get the ciphertext, we send it over so that anyone in between that might intercept that information cannot know what the plain text was, and we can use an algorithm again to get the plain text back when you want to. All right, so there's three main goals when we talk about cryptography. They're confidentiality, integrity, and authenticity. Confidentiality, or you can also call it secrecy, is basically, as I mentioned, Alice here wants to send a message to Bob, and Eve is looking at whatever the communication between Alice and Bob. And the idea is Alice to send the message in a cryptic way so that Eve, even if Eve is listening to every single thing that's going in between, Eve cannot know what the content Alice is sending to Bob. The next one is integrity. Integrity basically says that if Alice sends a message to Bob, then that message cannot be tampered with. That is, if Eve in the middle, or we can call that person Mallory because it's malicious, if that person in the middle decides to change that thing, we have to have some way of knowing if that thing was changed or validating if the encrypted message we received is actually valid or not. Lastly, we have authenticity. This one is basically saying that if Alice sent a message to Bob, Bob should be able to know for sure that it was sent from Alice. This, in some systems, is not too desirable, but in some systems it also is. Now, there's two principles that a good cryptographic system should have, and the first one is Kirchhoff's principle. Basically, the idea is that if everything except the key, that is like the ciphertext, the actual algorithm, how the thing works, and everything else of the system is known, accept the key, the algorithm should remain secure. That is like if the algorithm somehow should not be leaking how the ciphertext is made, so that if the as long as the key is safe, you should not be able to deduce what the actual content is. Shannon's maxim basically reiterates this thing, which basically says security through obscurity is not a good idea or does not scale. Obscurity meaning like just making it look complicated, however, it can still be reversed. So being complicated does not mean it's secure necessarily. Okay, when we're analyzing cryptography like a system, we can think about 5 different types of attack or actions somebody can do, and we can try to prevent or make measurements that prevents those or like gets around those attacks. The most simple one would be cipher only attack, COA, if you want to make an acronym. Is basically as the typical setup goes, Alice is here, Bob is there, Alice wants to send a message to Bob, and the attacker in the middle intercepts the ciphertext. But the only information the attacker knows is the actual ciphertext. So this is not too useful in like actual most of the really secure crypto systems. But if the one in the middle somehow is able to identify like a pattern just by looking at the ciphertext, then this attack would be valid or efficient. And then there's a known plain text attack, which is a scenario where basically the attacker knows like a plain text and a ciphertext combination or pair. And this way, it's a little easier or a little more obvious for the attacker to be able to analyze, okay, if a plain text has like a sequence of characters, let's say A and H, then the ciphertext will have X and C. If those informations are there, maybe the attacker in the middle can intercept like a new ciphertext and decode that or use it for malicious purposes. Next one is chosen plaintext attack. This one is fairly, this one will be our point of analysis later on. So the idea is attacker to be able to send a plaintext to Alice, and Alice will give you the encrypted ciphertext. And again, the idea is for you to make a very specific plaintext, send it to Alice, get the very specific ciphertext, and be able to analyze a pattern or compare it to like a pair that you know or something like that, so that you can decode the desired ciphertext that's being sent to Bob. The last completely different category would be chosen ciphertext attack. It's very similar to the last one, where the attacker can send a ciphertext, and this time Bob will decrypt that chosen ciphertext. I mean, obviously, you can't send the thing that we want to decrypt to Bob directly, and you like the answer would be that would be too trivial if you're able to send the message from Alice and just send it to Bob, and Bob will give you that answer. The idea is that you can send other types of other things, other ciphertexts to Bob that are different, but still be able to analyze um, the patterns or noticeable thing features. And this one probably is quite common or more most effective in some cases is chosen cipher slash plaintext attack, CPCA. Yeah, the idea is just to combine, like, there's no reason for you to only be limited to doing one of them. So why not talk to Alice to get the ciphertext and also talk to Bob to get the plaintext given like a specific ciphertext or plaintext. So yeah, the idea is just to combine those two methods and try to do two things more efficiently. Yeah. So now that we looked at different types of attack,
I'll just do a health check real quick.
yeah.
Okay, audio is working. Yeah. All right, looks good.
All right. We're gonna look at some encodings. Only 2 of them. Basically, encoding is just the idea of taking like a little sequence of bytes or something and just giving it a meaning. If you want to explain it pretty vaguely, and the ASCII should be pretty familiar to a lot of you guys. And yeah, so it's just a really specific set of mappings from sequence of bits into a character. The encoding that's notable is base 64, which is used when you want to transfer like a text-based data. Suppose we have a really cool text, literally, a really cool text. When you encode it using base 64, you get this UMVH blah blah blah. How this works is that you take the text and the text will be translated into, in this case, will be ASCII. MAN is that number, and you split it into 6 bits of chunks. And each of these 6 bits is mapped to a very specific letter. In this man example, those are mapped to TWFU. And if you notice the little the equal sign towards the end in really cool text, and also the example of high, that means that when you're splitting into 6 bits, there's no reason for every single text or data you want to send will be a multiple of 6-bit long. So if you're missing some of the bytes, you can add an equal sign to compensate for that, and basically just a padding. So here is a table. You can see base 64 means there's 64 possible values, which are all mapped into pretty cool, not cool, but readable text characters. Yeah, of course, there's 6 bits, 2 to the 6, 64. Possible ways you can assign alphabets. Yeah, now that we covered the basics, we can look at the ciphers, different types of ciphers. Firstly, we'll look at symmetric key cryptography. Symmetric key cryptography is basically the idea of taking a key and choosing one key, a singular key, and use it for encrypting and also decrypting. So if you look at the diagram, you get the message or plain text. You use a key to encrypt it. You send it through like a network, and then of course, since it's encrypted, if someone in the middle gets it, they shouldn't be able to identify that. And then use the same key to decrypt when Bob gets the message. There's 2 main types of ciphers: block cipher and stream cipher. Stream ciphers, we'll talk about it later on, but yes, it's not. There is kind of niche discussion around that. So almost everything in cryptography, arguably, is depending on this operation called XOR, exclusive OR, which, you can see the truth table for this. The idea is that if you have A XOR B, and if A and B is different, you get 1. If A and B is the same, you get 0. And the important property about XORs is that if you take X, XOR to Y, and then XOR again, it's equal to X. That's because Y XOR X will always have the same bits, meaning it's going to be, Y XOR Y will always have the same bits because it's the same things. And then if you XOR each other, XOR itself, then you get 0. So X XOR 0 equals X. Yeah, so the basic cipher you can derive from using the properties of XOR is called the one-time pad. If you take the plain text here, 10110100, and say you choose a specific key, 011010111 here, and you XOR this thing, then you can see that in the first row that the actual data changes. And the idea is that if this key is not known, then you cannot recover the plain text. Of course, you send this 1101111 to Bob, and then Bob gets it. And if you XOR again, as we mentioned, should be returning the actual plain text. So the important part about this one-time pad is that it's really simple, which is really cool, and it's very effective in a sense that the only thing you did is XOR, but the attacker or the Eve cannot listen and identify the plain text. However, you have to use a different key every message. If you use the same key, you can use the property of the XOR to gain information. Basically, if you sent a plain text A and then use the same key to also send plain text B, what you can do is some XOR things. and then you get A XOR B, which in most cases is not very good. Will reveal a lot of information about the plain text. Yeah, so I went ahead a little bit, but there we go. That's the reason why that happens, is that if the key is the same, if C prime equals, here it's M prime XOR K prime. However, if that K prime were to be K, then C XOR C prime would be M XOR K, M prime XOR K, and K XOR K is 0. So that would be M XOR M prime, and M, of course, here is a plain text, and you can get information about the plain text XORed with another plain text, meaning if you have one of the plain text, you can recover the other plain text too. And also in most cases, again, as I said, you can just discover a lot of features of that plain text, even if you only have the XOR. And another thing to note is that this one-time pad is impractical. You might have noticed that if you have to generate a key every single time you want to send one message, then that's not very efficient. And another thing to note is that the key has to be the exact same size as the cipher of the message. If the message is like 100,000 bytes long, then the key also has to be 100,000 bytes long. And imagine generating that 100,000 bytes long key every single time you send that message. So it's not quite impractical. I mean, it's not quite practical. Yeah, and let's look at some implementation that uses a key that's smaller than the message and also is still secure. So a notable cipher method is block ciphers. It's a symmetric key cryptography. You take this plain text and get the blocks. Basically, blocks is just chunks that I mentioned. You just split it into chunks and then encrypt each chunk into something else that's not recognizable. Like red is mapped to this gradient of red and blue. Yellow is mapped to this gradient of blue and Turkish color. I'm not entirely sure, but yeah, that's the idea. So each block is encrypted into another very cryptic block. The most standard, as the name suggests, block cipher would be Advanced Encryption Standard. The NIST, what they did from 1997 to 2000, if I'm not mistaken, they held like a contest, and in that contest, they wanted to choose like a new, really good cipher so that everyone in the world can use it as a standard. And there were a lot of candidates, and the one that was chosen is this. And it was standardized in 2001 after that. After it was chosen, after analysis of which one's too fast, or which one's too slow, or which was too insecure, which was not practical, etc. And without getting in too deep about how the math actually works behind AES, I think it's just worth discussing the ideas of how this thing works without getting the nitty gritty details. So there's this, you start with this method called key schedule. Key schedule, you can also call this expand key or key expand, which is the idea is to have a key that's 128 bits or 192 or 256 bits. You have a key of specific length, and then if you call key schedule, you're going to have you're going to generate a bunch of different more sets of keys from that one key. And say you want 10 different keys, then the key schedule will return 10 different sets of keys that's generated by the one magic initial key. After you generate those 10 different keys, you can do a sub bytes, which is basically, so okay, the 4x4 table is a block. You can arrange the 16 bytes. If a block is 120 bits long, then there's 16 bytes. You can arrange them into this 4x4 matrix or table. Then you can get each value and call subbytes. And what subbytes do is that it takes the value of the byte and then substitutes it with another value, just swaps it out. And this value that's being substituted is just predefined and it's pretty publicly available. And after you change them up, what you do is shift rows. What shift rows does is basically it shifts the first row by a certain amount to the right. It shifts the second row by a certain amount to the right, and the third row and the fourth row. So it shifts and mixes up the order of the things, of the squares basically. And mixed columns basically takes each column, the vertical, for things, and then combines them in a very certain way. So yeah, and then this again, this is just trying to mix things up as the name suggests. And after doing all that, you add round key, which basically does the XOR that we already know. But because this is doing, we generated 10 different sets of keys, we're gonna do add round key of that specific iteration. So if it's the first time you're doing add round key, do add round key once with the first set of key, and then if you're doing this loop second time, then you're gonna use a second key. And then after you do all this, without being too specific, you're gonna have a ciphertext. And the idea, the reason why this cipher is so complicated or has so many steps compared to the one-time pad we just saw is um, we have to have two properties defined by Cloud Shannon. One is confusion. Confusion basically says if you have a plain text and a key, and then you change the key by 1 bit, then the actual ciphertext, the result should be changed noticeably. That is, if like the idea is that if the attacker changes a plain text by 1 bit and notices, or even the key changes by 1 bit, and then the ciphertext changes by 1 bit too, then you can clearly see, oh, this fourth bit is related to this third bit in the ciphertext. Okay, I can relate those two. And then you can repeat those process to maybe find like a property or like the actual key, and that's not very desirable. So the idea is for the actual encryption process to depend on multiple parts of the key, multiple bits of the key. And that's the reason why we just generated those 10 sets of keys so that we can depend on the key in many different aspects. Now we have diffusion. That's the second property defined by Cloud Shannon. Diffusion, the idea, I think I kind of mixed up when I was talking about this, but if plain text changes by 1 bit, the actual result should be changed ideally at least around the half of the ciphertext. Again, so yeah, so just so that the attacker cannot recognize a pattern. So the reason why this data encryption standard or like advanced encryption standard has been published is because the previous generation or the previous iteration of this system, which is called just DES, data encryption standard, was no longer secure. That's mainly because the key is 56 bits. I mentioned pretty quickly earlier that the key for AES can be 128 or usually 256 bytes, I mean bits, not bytes. So if it's only 256 bits and with some intelligent hardware, I mean not hardware, algorithm with modern hardware, you can brute force this old algorithm, DES, in less than a day. So, but of course, there's a lot of legacy systems that's still using DES, like Fortran systems or like COBOL, finance industries. So you still want to support DES, and what was proposed is 3DES, which essentially just applies DES 3 times so that it's 3 times as more secure. That's not too precise, but that's kind of the idea. So that your key, there's 3 different keys that used, 56 times 3, that's more than 56, meaning it's more secure. But this is too slow. So if you're making a new crypto system, of course, you should probably be using AES or another more fast and efficient algorithm. Okay, and now we'll notice a pretty big flaw in block ciphers. And block ciphers, of course, AES, what we just saw is like you have to put the message in, the message has to be 128 bytes, or why am I keep saying bytes? 128 bits for it to be put into a 4x4 table. And I mean, surely when you're sending messages, you have a message that's longer than 128 bits. If you have a message that's longer, then what you have to do is you have to decide on how you're going to separate these or how you're going to chunk these up so that we can apply this block cipher that we just figured out. And we're going to look at three different types of things you can do in order to send a longer piece of messages. And the first one, the most obvious that anybody can think of, is just take a long text, split it into the desired amount of bytes or bits, and then just encrypt each of them one by one. This is pretty nice. It's pretty easy to implement. The problem is, you might have noticed there's a picture right here. The problem with ECB is that it maintains the order or the structure. You can see the tux, the Linux penguin right here. That's a main original data. Even if it's encrypted with ECB, you can see that you can still see the penguin shape. Of course, this is not a sensitive data or anything, but if you have a sensitive data and you sent it, but you can still identify like a structure, that's not very secure. Ideally, you'll see on the third picture, that's just complete just nonsense. That's what you ideally will be wanting. So there's a lot of ways to attack ECB, and one of the main notable ones is Oracle attack. And the Oracle basically is just this cool or this figure that performs the encryption of a specific plain text for the attacker. Just like the thing we just talked about, we're just asking Alice, for example, to encrypt this little plain text for me. Uh, we're just talking in the perspective of Eve or Mallory, the bad person. So the idea here is that we're going to feed in the B here is a block size. We're going to feed in the block size minus 1 byte of the data that we know. And then what Alice is going to do, what the Oracle is going to do, it's going to append this little S0. S is a secret that we want to decrypt. It's going to append that S0 and give us the CR1, or like the first crypted text. If we have this, then now that we have the now that we isolated this S0, what we can do is basically just send another A, which is A0, A1, A2, the exact same thing, but change the last bit. Now you're sending byte, a B bytes long message, so that you can kind of guess and check what S0 can be. A byte is 8 bits long, so you can brute force those quite easily because you're only brute forcing 1 byte. And then now that you have S0, if you have S0, you can repeat the exact same thing by brute forcing S1 by shifting it a little one more. And then you can brute force S2, and then you can brute force S3, and so on, and just keep attacking. And what happens is that typically, if you have a block of 16 bytes and you just want to brute force without any uh, optimization or ideas implemented, just naively, then you have to have 256 to the 16 checks. You have to check every single one of those, and that takes a really long time. But if you do this Oracle attack, then because you only have to check for 1 byte at a time, you only have to check 4096 combinations. That's a lot less than 256 to the 16th power. So this would be a pretty effective attack when ECB is used. So there's another method you can use to split up these long messages and still use our cool AES or any block cipher methods, is to use CBC. CBC is cipher block chaining, and you can see you're chaining the things, chaining the previous ciphertext to the next ciphertext block. So the idea is to choose an initialization vector and XOR that with the plain text. And you encrypt this XORed value to get the ciphertext. And this ciphertext, say ciphertext block 1, is then XORed with the second block, second plaintext block, and then this value is encrypted. So it's like a staircase where the previous ciphertext block is used to encrypt the next plaintext. This way, the structure or the example we just saw, the penguin, will not be too obvious and it will be hidden. So these kind of attacks where you just sit there and analyze the patterns will not quite work well. One thing to note here is initialization vector cannot be predictable. If someone that's bad is able to predict what this initial value of the vector is, then they can again use XOR shenanigans to get plaintext XOR plaintext. And again, that's not very good. However, it's worth noting that initialization vector can be just public, does not have to be hidden at all. All it has to be is unpredictable. You just choose a new unpredictable initialization vector and do this thing again if you want to send a different message. Okay. However, of course, there's a attack that can be done. Here, there's no label. However, Alice is here. Alice wants to send this ciphertext you encrypted C1 to CN, uh, n blocks long message to Bob on the right side. However, you can see this red guy, Mallory, or bad guy, he decides to take this very particular value, x, and XOR it with C1 or CI. So any particular block he wants to attack. What happens is that if you XOR with your own data, which is x, you get this value m. And of course, if you now that you replace that block with your new XORed block or data, Bob is just going to get C1 dot 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 m dot 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 Cn. What happens if you do that is this C1 XOR x will be decrypted, of course, we will decrypt it and then XORed again with the previous ciphertext to get the value. But the actual ciphertext we're decoding was XORed with this bad value x. So the thing you get is garbage. So, and then what happens is that this garbage does not matter. The thing that we desire, the outcome we desire, is in the next step when you're decrypting the CBC method. So this ciphertext C1 XOR X is used to decrypt the next cipher block. As we mentioned, we're chaining the things. And the next cipher block is decrypted and then XORed with C1 XOR X. That's not good because, of course, C1 XORed with a decrypted block of C1. Why am I keep saying one? Please replace all the ones that I've said so far with I. But the idea is CI XORed with CI plus 1 is XORed, and of course, that returns the correct PI plus 1. XORed with X because XOR X is still there. And what this means is that you can just XOR any block that you want with any data you want and just XOR the plain text that Bob is going to receive. This is not good because the idea is that X, you can just flip any bits that you want. And if you can flip bits, you can flip specific values like a Boolean. And if you flip a Boolean value that maybe changes you to the admin, then you just became the admin by doing this. Okay, and there's the last one would be counter mode, CTR. Here we have this value called nonce. And here we take this value n, nonce, and then we append it with a counter I. I would be the number or the ith block, that index of the block. And that number is just padded with 0 so that the actual data we're using is regular. And we're using this with the key to encrypt the plain text. And by doing this, of course, like P1 would be N00001 used with the key to encrypt P1, getting C1. P2 would be N00002 with the key used to get C2. And here, again, like the initialization vector, one thing to note is nonce, this time, can be predictable. However, you cannot use the n again. That is, you can't use the same value of n again. If you used the value 13 yesterday, then you cannot use it today, because if an attacker is very observant, then he'll be able to do, again, XOR things and get some data or plain text ideas. Okay, that was basically it for symmetric key cryptography. And the thing that I talked about with stream ciphers is that stream ciphers are you could talk about block cipher mode of operation as string ciphers, but there are ciphers that are designed to work with really long things by default, instead of block ciphers being like an one step to that is used to extend the actual like long method. But string ciphers are not commonly used in modern practices. So yeah, block cipher or block cipher mods of operation is what's actually being used with AES or any really good encryption standard. And so we're just going to move on to asymmetric key cryptography. You might be able to guess that if there's symmetric key cryptography that uses the same key to encrypt and decrypt, probably there's a method where you encrypt with a different key and decrypt with a different key. The notable ones are RSA, DHKE, and ECC. We're going to look at RSA and ECC in detail. Yeah, so again, the idea is just to use a public key to encrypt the message, and only Bob, who gets the encrypted message with the public key, can decode this message, because Bob is the one who generated the keys, and Bob is the only one who knows the keys. Yeah, that's basically just a visual about that. And how this works is that we first have to understand a discrete logarithm problem. The problem basically just says if you have this relation a to the x is equivalent to b mod n, then can we find, and we're given the value of a, b, and n, can we find the value of x? This turns out to be pretty difficult without some use of theorems and stuff, and that theorem only applies in a very specific case, which is why this algorithm will be working in our favor. So a side note is that there's a lot of different types of hard problems that are difficult to solve for the attacker or one that's just listening in the middle, but fairly easy to solve for us that know like a very specific part of the information. There's a discrete logarithm problem, DLP, that we just mentioned. There's elliptic curve discrete logarithm problem, which we'll discuss later quickly. There's short vector problem, and there's learning with errors problem, and there's many more. And yeah, we're just gonna be looking at the first two today. RSA, being quickly, is basically given P and Q, which are prime numbers. Bob generates these P and Q, really big prime numbers, computes this value n, which is a product of two primes, and this value of n, and then we compute this function, the Euler-Toshin function, which is basically phi of n equals the number of positive integers that are co-prime to the number n. And after some proofs and stuff, you happen to know that if n equals a product of prime like that, then phi of n equals p minus 1 times q minus 1. And you use this phi of n to get e, which stands for exponent, such that GCD of e and phi of n is 1, or they're just relatively prime. And there's D, which is a private key, which is a modular inverse of phi, E mod phi of n, meaning if you take E and if you take D and E, multiply them together, and divide it by phi of n, you're going to get remainder 1. We're going to see how this is helpful in our case. So again, the public key in this context will be the E and the number n, which is P times Q. And here, when you're encrypting, since the public key is E and also N, we're just going to take the plain text, raise it to the power of E mod N, that's a ciphertext. And if Bob gets a ciphertext, he can just ciphertext to the power of D mod N and just recover the message. Yeah, so here you can basically see some implementations of how to use these numbers to actually talk about RSA. But yeah, since I have talked a little slower, I'm just gonna forward through this. And the idea is that if you know the Toshin function, or AKA knowing n equals p times q, then you can basically just crack the RSA algorithm. Meaning that RSA relies on the fact that n equals p times q, given just the value n, it's very difficult to find the two really big prime numbers that makes up for that product equaling n. So a attack you can do is when a person uses the same modulus n when you're encrypting. And you can break these because, again, you can use some math here. Uh, Here, one thing to note is there's something called Bezout's identity, which is basically if you have GCD of some numbers, and that means you can write that GCD as a linear combination of those numbers. And if E1 and E2 has GCD equals 1, then that means there are some integers, A1 and A2, such that their linear combination of E1 and E2 equals 1. So we can abuse this by taking, if ciphertext C1 and C2 is there, you can take C1 to that exponent and C2 to that exponent, that those are coefficients that gives you the Bezout's identity. That means that since C1 was equal to m to the E1 mod n, and C2 was m to the E2 mod n, we get E1 times A1, E2 times A2, laws of exponents. That means you're adding them because you're multiplying. Then again, because of Bezout's identity, that means that's equal to 1, and then you just recovered the plaintext m. And this would be an implementation. The implementation looks slightly different than the math because you have to deal with situations where here A1 and A2, as I said, is an integer, so it can be positive or negative. So you kind of deal with those with using modular inverses and stuff. There's also another type of attack called Wiener's attack, and what this basically does is that you take the fraction, I think it was n over d, or d over, I think it was n over d. You take the fraction n over d, and then you use some math things to be able to derive the value k over something, meaning that you can get the value of k. So yeah, the idea is that your d should also be really big, so it's difficult to brute force everything. Yeah, we're almost done with this stuff. Almost the last topic is Diffie-Hellman key exchange. And this key exchange algorithm is that we've been talking about how symmetric key cryptography uses the same key to encrypt and decrypt. But then the question that comes is that how do you share the secret key to Bob in the first place? Like, if you don't have a method already set in stone to share, then that key, you can just intercept the key and you'll be insecure. Like, there's no point of doing cryptography. So the idea is to make a way to be able to share this really important secret key without exposing the secret. So what happens is that here, let's say blue is Alice and green is Bob. So Bob generates this very secret value beta. Alice generates this very secret value alpha. Bob computes G to the beta mod m. Here, G and M is just like really random public key that's agreed upon beforehand. It can be public, like it doesn't matter if the red guy listens to it. Then Bob sends G to the B mod m, and G to the beta mod m, and Alice sends G to the alpha mod m to Bob. Then that means since Alice knows alpha, you can compute G to the beta alpha mod m, and Bob can compute G to the alpha beta mod m. Of course, G to the alpha beta and G to the beta alpha is the same thing, and they get the secret key. But even if this red guy, E, was sitting in the middle the entire time, the only thing he knows is the public key G and M and the value of G to the beta mod m and G to the alpha mod m. And you can't really recover that value, G to the alpha beta mod m. And the last one we are going to look at is elliptic curve cryptography. The math behind this is somewhat complicated, so we're just going to look at the major ideas on like what this might be about. This is just another way of making a very difficult to solve problem for the guy in the middle to solve, but it's easy to solve for us that has that little D information that can decrypt. Yeah, this is apparently used in iMessage, Bitcoin, and Ethereum. And yeah, here, so what an elliptic curve is, it's basically an equation that makes these type of curves that is like elliptic. And what's important here is that you can define the points P and Q and connect those two such that they form a line. 2 points form a line. If you make 2 points, there will be another point R which intersects with that elliptic curve, and we can define this. This plus is not the same plus that we usually see, so we can define this operation called P plus Q equals R equals minus R, where minus R is just a reflection of that intersection of the line R along the x-axis. So technically speaking, this operation and stuff forms a group. And what ends up happening is that we can form this problem. Given the points P and Q, such that Q apparently equals some number that we don't know, Kp, which is basically P plus P plus P doing K times, can we find K? So what happens is that we only share the value of P and Q publicly. And then for the red guy in the middle, to figure out the K, you have to, it's not easy to actually figure out the K. Yeah, and that's the idea. The reason why we use this in the first place is apparently elliptic key cryptography is has a lot is a lot more difficult to brute force than the standard G to the alpha beta, those type of modular arithmetic based problems. And yeah, that's the reason why this exists. And there is a table that's more specifically saying those data, volume of water to bring to boil, meaning like how much water you're going to waste by computing that thing. But yeah, that's basically the idea behind asymmetric key cryptography.
Or like, it's not very heavy, but there are a lot of implementation details. So the way you design a hashing function is not very pretty. We'll get into what that looks like later on, but it's not very pretty. So you've probably heard of hashing before. The idea behind hashing is that you have a function that is going to take an input message of like arbitrary length and return an output message that is fixed length. So some of the key properties of a hashing function is that it is non-reversible, or tries not to be reversible. There are specific attacks that we can talk about later on that try to reverse things. It's called the preimage attack, but most hashing algorithms should try to be non-reversible. So like, if you think about a non-reversible algorithm, maybe think about like modulus, which is like, it's hard to find the original input because there are different inputs that it could actually be, or it's just a very convoluted algorithm. It also wants to be fixed size, and it also wants to be unique. So you don't want the hashing algorithm to have collisions. What this means is that you have your message, two different messages, and they produce the same hash. So you want to try to avoid that. So that's the basic idea of a hashing algorithm. We're going to go over a few of the examples later on. Specifically, you can use hashes for a variety of things. So hashing is really good for programming if you are making like a hash table, for example, or doing some compression things. Hashing is really useful for that. In terms of security, we care about hashing for integrity. So sometimes, let's say we have this message here that has this hash, and then this message here that is modified very slightly, mouse 72 versus mouse 73, modified very slightly. You want to change you want to check the hash to see if the messages are the same. And because they're different, you can sort of understand that the original message is different as well. So we tend to use hashing a lot for integrity. That's the main thing, but we can also use it for different cases as well. So yeah, there's this algorithm called MD5. The idea is that it's a hashing algorithm that works with a 512-bit input and produces a 128-bit output. Now, there are a few cases that you can do if the input is not 512 bits. If the input is smaller, then it can be padded. If the input is larger, then you can run MD5 several times for each 512-bit chunk. So kind of similar to what we did with symmetric cryptography with the ECB mode, you would just split it into several chunks and then run the hashing on those chunks as well. So the algorithm is very convoluted. I will just kind of briefly have a high-level overview. So the way that it works is that you have a state. You kind of have a state, an internal state that starts initially hard-coded. So you have a value of A, B, C, and D that are initially hard-coded, and you want to perform some operations to scramble the state. And then after you perform that, your final state, which is the hash output, is going to be the concatenation between A, B, C, and D. So what you actually do is you perform 4 rounds, And throughout these 4 rounds, you iterate through the plaintext message. So your message is, remember, 512 bits. You can split that into 16 chunks. And then you want to iterate it through different ways. So the first one is you iterate it through it linearly, so I plus 1. So for every I to 16 in that range, you perform a round func. And we'll talk about the round func is in the next slide. For the second round, this should be round 2, round 3, round 4. I did not, this is a typo, but the second round, you are iterating it with this modulus here, so 5i plus 6. So you're starting at like 0, and then 5, and then 11, and then on and on and on. So you're going through it in different orders, and then so on and so forth, different ranges of how you can iterate through the plaintext list. It is kind of messy, but it provides a lot of confusion. So you also have these hard-coded arrays K and R. They're used for different purposes. The array K is used for XOR operations, and the array R is used for rotation. And you would just access a specific element of these arrays during the round function. So the round function, this is what it is. You don't have to understand how it works. In fact, you don't have to memorize how this works. Just have the basic understanding of how this algorithm could work, and understand that what it's doing is it's causing a lot of confusion all across through these non-linear operations. So you have your current state here, and you want to get the next state. And how you do that is you perform different operations on different values of the initial state. So for example, C, the value of C is just B. It's just a previous B value. The value of D is just a previous C value. The value of B is going to be the value of A XORed with C, XORed with D, XORed with an item in the hard-coded array K, which is the XOR array. So if you take a look back here, this is the XOR array. You are grabbing an index here, and you're XORing with that. Sorry, RI is like a left rotation, and you're grabbing it from the hard-coded rotation list. And then you would XOR that with the value of B, and this is the new B. And then A is just the value of D. And obviously you're taking the plaintext array and you're XORing it somewhere here. So we have a workshop between 4 to 6. Yeah. Ends at 6. Yeah. 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 Okay. So if you're curious on what this is, this block here, this is addition in mod 232. Is it XOR? No, it's addition. Okay. This is addition in this finite field. So this is actually addition, not XOR. So yeah. So the idea is that if you want to create a good hash function, you want to reduce hash collisions. When different inputs in your specific algorithm cause the same hash, that is a bad idea. That's a signal that your hash algorithm is not really good for security. Now, the problem with MD5 is that it's actually very easy to produce a hash collision because the algorithm does not actually scramble enough. So this is an example of a hash collision. You can see that an A and an E is different, and they produce the same hash. So if you rely on hashes for secure integrity checks, then a hash collision is very dangerous. And in fact, you can actually crack and find a hash collision given a hash and a message. You can find a different hash collision in less than 1 second with MD5, if you were curious on how that works. So MD5 is not very suitable for the things that we want because of the hash collisions. Yeah, so that's the basic idea. Right. So there is, I think, let's go to the next slide. Yeah. So there's been a case where there was a malware, the Flame malware, that used the MD5 collision to forge the Windows code signing certificate. So it is very easy to find a hash collision and also use that hash collision to sign other pieces of software. So the reason why we don't trust MD5 for anything secure is because the collisions are very easy to find. So there is another idea that you can actually attack a hash by looking at the digest and trying to find the inputs that cause the digest. Now, realistically, this is very hard to perform practically, so this is a theoretical attack, but it's something to keep in mind that a good hash function should be resistant to these types of attacks. So in most hash functions that we use, like MD5 and SHA-1, There are no known pre-image attacks, but it is something to keep in mind that you want to avoid finding some easy way to find the input to your hash function. There is a second attack, which is a second preimage attack. That is also something that you should keep on your threat model, on your radar, which is essentially you have the hash digest, so the output of the hash function, and you have another input that causes that digest function, and you want to find a hash collision. So you want to find the different input that causes the same digest, which is similar to what we did in the MD5 case to find the actual hash collisions. You want a different input for that as well. Now, depending on your threat model, you might not actually care about a second preimage attack. So an example is with Git. The way that Linus actually developed Git is that in case there was a hash collision, what you would do is you would just check the date of the commit. So I believe Git actually uses SHA-1 for the hash commits. So in case of a hash collision, you would just check the date, and that you would just take the one that was earlier on as the commit to follow. So yeah, so those are some attacks that are in your threat model, your theoretical attacks. There is this hashing algorithm, there's this collection of hashing algorithms developed by the NSA, SHA-0 to SHA-3. So so SHA-1 is a revision of SHA-0. It is very similar to MD5, so there's a 512-bit input, and it creates an 160-bit outputs. It is slightly more expensive. It has the same idea. So like if your input is not the 512-bit size, you can pad it. If it's larger, then you can run it several times as well. Okay, so if you're curious, this is the algorithm. You can see a lot of similarities to the MD5 algorithm. And the reason why this is, and okay, I'm not going to talk about this because this is just convoluted. You can kind of piece together what the diagram means. There's these rotations, and then there's some more additions in finite spaces, and then you're iterating for plain text. It's pretty much very similar to MD5. The reason why it's similar is because we developed a hash function with something called a Merkle-Damgard construction. So this is a type of way to create a hash function. What you do is you have this idea of a compression function, which takes two inputs and returns a fixed size output. And then the subsequent hash that you're producing is going to depend on the output of your previous compression function. So you're taking inputs from the plain text and you're feeding it into the hash function. And you have an initialization vector, which is given as the first input for actually starting it. Get this initialization vector from a random number generator or something that you store somewhere. And you would use that output to feed in as the next input for the next compression function. So it's very similar to what you see here, where the previous state is going to be used for the next state as well. So, and you're grabbing from the plain text as well, which is you're grabbing from the plain text up here. So this is the idea of a Merkle-Damgard construction. Now, the idea behind the Merkle-Damgard construction is that it can also be vulnerable. So we don't actually want to use these there was like a classification of vulnerabilities found that are length extension attacks. And it is a vulnerability specific to Merkle-Damgard hash functions. Now, the basic idea is that if you have the hash of a message and the length of the message, then you can get the hash of the message plus some arbitrary bytes. You can get the hash of this. So you can get the hash of essentially any message you want, given that it's appended to the first message. And this is very problematic when we talk about message authentication codes, which is using hashes to check the authenticity of messages. So the reason why this is happening is because, well, in a Merkle-Damgard construction, the output is dependent on the previous, or like the next bits of the hash output are dependent on the previous inputs. So you can find the next hash output because you have the hash output of all the previous ones. So if you just have a message that is extended on, well, you can use the hash output of the previous one to actually get the hash of the next one. So that's the basic idea there. Now, there are a collection of hash functions that are not vulnerable to length extension attacks. And this is what SHA-3 is based off of. And the basic idea is that you have a capacity bit here in the input that is going to be used to regulate how large the hash can actually be. So there is an absorbing phase, which is taking in the plain text message, and then there is a squeezing phase, which is used to generate the hash outputs. So this is what's used in SHA-3. But we're not going to go into SHA-3 because that would be, I guess that would be too long. So yeah, so a good usage of hash functions is for integrity, but there's a problem with using hash functions only for integrity. So let's say, for example, we want to send a message across the network and we want to ensure that the message is not being tampered with. So we include a hash and the message. And so Alice will send a message and a hash to Bob. So during the actual traffic, while it's in transit, Eve intercepts the message and they change the message and they hash the message and they change the hash to the hashed version of the message. Well, then when Bob receives the message, they check the hash of the message with the hash that they were given, and they match. But the message and the hash are both changed, so this doesn't actually work. So how do you actually guarantee integrity across a network? Well, what you have to do is you have to have your secret key, which is something that the man in the middle doesn't know. And you want to include that inside of your hash function to produce a MAC checksum. So having the secret key would allow you to encrypt something, or I mean, hash something, and then be able to verify later on. So let's see an example here. In a MAC, what we do is we take the message and the key, we combine them, and then we create the hash of the combination between them. So this is the MAC here. So let's say Eve now takes the message and the MAC and changes the MAC. Well, the thing is, Eve cannot compute the MAC because she doesn't have the secret key, right? Alice and Bob both have the secret key, but Eve does not. So the hash that she produces is not going to be the same one that should be produced with this message. And then when Bob goes to verify, he adds his message, he adds the key to the message, and then produces a different digest. And it compares it with the MAC, and it is different. So this is the basic fundamental idea of a MAC. Now, how do you actually create a MAC? So there are a few ways, there's a few ideas on how you can actually combine the message and the key. So let's say, for example, you want to add the message with the key, so the key is after the message, so you just append it afterwards. Or let's say you can prepend it afterwards. So these are different ways that you can actually create a MAC. So if, for example, you were to prepend it, then you would add the secret key and then add it to the message, and this is the secret prefix. And then the secret suffix method is you have the message and you have the key and you would append it. So these are two different methods. There are some problems with this. And the reason why we don't actually do this, we actually use something else, which is called an HMAC that we'll talk about later on, is because these are vulnerable. So if you remember previously, the length extension attack, the problem with Merkle-Damgard is that you can take your the message and then you can add your own message at the end of it and then get the hash of that. Well, this is a problem if you were to use the secret prefix method, which is you're adding your key and then a message here. You can continue adding on to this message and you can continue hashing it because of the length extension attack. So this is an example. Alice sends the message and a MAC, but she's using a length extension vulnerable hashing algorithm. So what Eve would do is she uses the length extension attack to increase the message and then overwrite the hash. And hash is going to be the same because of the length extension vulnerability. And so when Bob goes to verify, the MAC is the same as the message. And so this is the problem with the secret prefix approach. Now with the secret suffix approach, which is when you're adding the key at the end, there is a vulnerability with potential hash collisions causing the same message. So this is called forgery. So if you have the same hashes for two messages, then you're also able to find the message authentication codes between them as well. So this is specific to the secret suffix. So how do we prevent these attacks? Well, there's an implementation on how to combine the secret key and a message such that it doesn't fall short. It doesn't have these vulnerabilities that the previous ones do. So this is called the HMAC. And so how it works is that you have your key and you're going to extend it to the block size. So you extend it and then you pad it out with this constant stream of bytes. So OPAD is just constant stream of bytes, 0x5c, on and on and on and on. And then you append it to the hash of your key, sort of IPAD, which is this constant stream of bytes, appended to the message, and then you hash all of that. So the basic idea is you hash it 2 times. This is to prevent any predictable behavior because you're hashing 2 times. So yeah, I'll just check for any questions. It looks fine. Okay. So yeah, so that is hashing algorithms. We're going to talk about pseudo-random number generators, which are very heavily related to hashing algorithms. So I guess before I talk about this, the reason why they're related to hashing algorithms is that pseudo-random number generators are kind of based off of hashing algorithms. So if you look at the output of a hash algorithm, it is kind of arbitrary, it's kind of random, it's kind of not predictable from the original inputs. And so if you take that output and then continue feeding it in to itself, you can kind of produce random numbers. So that's the basic idea behind a pseudo-random number generator. What you're going to do is you're going to have the input, which is some seed, some value that you ideally want to keep secret if it's a secure system. And you have some transformation function which changes the state, and then you produce some random bits on the output. Now, how does this transformation function actually work in practice is that occasionally you will take the input and then you will take the output and then feed it back as the input. So that is going to change the internal state as well. So nothing from a PRNG is truly random. So if you find a seed, then you can find the same random output that is going to be the same because the PRNG is completely deterministic. So yeah, so here's an example of a very simple pseudo-random number generator. It is called the middle square algorithm. What you do is you take the seed, you square it, and then you get the middle digits of the square value, and that's your output. Then you feed that output as the input, you square it, and then that is your new random value. So all of these outputs are your random values. So there is something that you might see in a lot of pseudo-random number generators is that because they're deterministic, if you end up getting the same input at some certain point of time, then you will just have a repeat of the output values. And this is a problem. This is why you want to ideally make your input as large as possible so that you make the period very long. But every single PRNG has a period. This is a vulnerability. If you can find this period, this is a problem because then you can just predict the next outputs. But what you do is you want to make your input very large. So there's a problem with the middle square algorithm, this algorithm back here, which is that it's not actually very good as a random number generator. So something that you want a random number generator to do is to have a uniform distribution of the results. So if you look at the middle square algorithm here, the distribution of results is not actually uniform, right? There's a clear bias towards some values. And you want it to be uniform because you want all of your outputs to have an equally chance to be returned. Because if you don't have that, then you just can confidently say that you're more likely to generate this random number than that. And that defeats the whole purpose. So yeah. Another pseudo-random number generator, one that is very, very fun, is an LCG. How it works is that you have your previous input and you multiply it by a multiplier, and then you add it by a constant, and you take the mod of that by a given m. And so that would be your output. So here's an example of how this could be used with your multiplier as 1014, and then your constant to add is 511, and then your modulus is 1011. Your initial seed is 42. Well, what you do is you put 42 as the x here, and then you times it by this, and you plus this, and then you mod this, and then this is your x1. And then x2 is you're just feeding x1 here, and then that's how you get x2. So you would take all of these and you would combine them into a stream, and then this is a stream. If you want a random number of bytes at like a certain length, then you just take a substream of these stream of values, and then that is your random number. So let's say you want to actually break an LCG. It's very easy to break an LCG. With your LCG defined as this, how do you recover the parameters? LCGs are not secure. If you didn't pick that up, they're not secure. So what you do is you want to recover m first. So you find un, which is, well, yn, which is the difference between the two, and then un, which is the one before times yn minus yn plus 1, and then m is the greatest common denominator between these with very high accuracy. If you want to increase the accuracy, you make k very big. You can recover a from this equation here. You just recover a very simply, and then you can recover c from this equation as well. So yeah, there was a real life scenario where a specific voting ballot system where you were going to vote for an electoral candidate was using a linear congruential generator. And what this allowed you to do is you could identify voters who was voting for what based off the time, and you could predict the specific identifier because the LCG was broken. So you could just predict the next random values and leak confidential voting data. So yeah, there are different random number generators. So there's this idea of a XOR shift, which essentially XORs and then shifts. That's the idea, right? You have your previous state, you XOR it, and then you shift it. You shift it by some amount, and then you XOR it. So that's the basic idea. There is a different one called a Mersenne twister, which is very common in programming languages. So if you're using JavaScript or Python, the default random implementation is actually a Mersenne twister. You have a initialization function which creates this grid, and then the twist function would convert this into a twisted grid. And what you're going to do is you're going to take a cell of this grid, and then you are going to run a temper function to get the specific output, some segment of the output that you want. And how the state is actually updated is that the twist function automatically increments itself so that the next generation is going to be different as well. But this has actually been seen to be broken to seed cracking attacks, because a very common seed is the number, wrong way. Okay, so a very common seed is the number 19937. And Mersenne twister 19937 has the combinations listed out. So it can be broken by just looking at 624 results. And we match that to the results that we gathered before with the deterministic random number generator, and then we can crack and find the original seed that was used. So this is like a Python library to crack it, and you just submit 624 results, and you would get the original, or you would get the next value. Sorry, you would get the next value that the random number generator would produce. Okay, and another good use of PureNG is actually to generate new keys. So let's say you want keys for, let's say, a key exchange. You could take a key and then add a salt to the very end of the key, and you would be able to generate more new keys based off that using a pseudo-random number generator. So it's a pseudo-random number generator under the hood. Yeah. All right, so if you're curious on how to get true randomness, well, there are a few methods. So you can use the driver noise. So like all Linux distributions have a dev random directory, which you can read from, and that would give you true randomness. There's also lava lamps and camera, which is what Cloudflare uses with the lava rand. There is noises in the real world, so you take a microphone and you just get random noise from the real world. There is coupled inverters, which is like a hardware solution that Intel is using. That is also pretty cool. So yeah, we're going to talk about the last thing. The last thing we're going to talk about today is PKI. And this is how you actually implement a lot of the things to ensure secure communication across the internet, pretty much. So before we talk about that, we have to talk about the digital signature. Now, a signature is essentially an encrypted hash that is used to prove one's identity. And what you want to do is you want to share your signature to everybody. So it should be public. And everyone on the internet should be able to look at it, and they should be able to look at your public key and should be able to verify that, okay, this message was actually signed by Alice. So yeah, so how it actually works is that if you have a signing algorithm, like for example DSA or ECDSA, they all work in this way. Wrong step. Okay, so they all work in this way. So if you are going to if you want to sign something, if you want to create the signature, what you do is you take a message and you hash the message, and then you encrypt it with asymmetric encryption algorithm, like for example ECC, the elliptic curve cryptography encryption algorithms, and you would put your private key, and that would encrypt it to produce your signature. So you would package it together to create your signed message package, which has the message and the signature here. If you want to verify what you can do is you can take the signed message and split it into the message and the signature, and you want to hash the message. So you want to hash the message, and you want to decrypt the signature with the user's public key. And if the hashes are the same, then that's how you verify. Remember with asymmetric cryptography that the private key and the public key are inverses. So you're able to take the user's public key and decrypt to have the same original message that was used to encrypt with the private key. So again, everyone can verify this given that they have signed message and their person's public key. Yeah. Okay. I think we talked about a nonce previously, but in order, like it's very commonly used in specifically digital signatures. You don't want the same signature every single time, so you want a nonce, something that increments every single time, and you want to sign it with the nonce plus the message, create a unique signature. And commonly, what you're going to do is you're going to take the nonce and share that nonce publicly. So, like with the message and the signature, you want to include the nonce in a package that you're sending as well. Okay, so signatures are kind of similar to MACs, right? Because they're both checking for authenticity. But the main difference is that you have the ability to communicate with anyone, so strangers. So if you remember how a message authentication code works, Alice and Bob need the same private key. So it is kind of like a symmetric way to verify things, whereas a signature is asymmetric, right? You need the public key, and that's all you need to do to verify. It also provides non-repudiation, and the idea behind non-repudiation is that you have some things that you can do, and you can't say that you didn't do it, because the idea is that it's unlikely that someone else has the same private and public key as you. So let's say, for example, you're a system administrator and you're going to SSH into a box. So everything you do is relating to your public key at that point. And so if you try to deny any changes, like let's say you delete some critical files while you're on the server, well, your public key is listed, and then everything you did was also signed, so you can't actually say that you didn't do it because it's unlikely that someone else has the same public key as you. So that's the idea of non-repudiation. Yeah, like the same public key as you and also the same private key, because in order to do anything you have to have the private key. But yeah, okay, so we'll talk about public key infrastructure now. So public key infrastructure is very convoluted. This whole diagram here is kind of a reduced version of that, but the idea is that you as a server, you want to ensure that you have a certificate, and the idea of a certificate is to show that your site and what you are is associated with an identity. So this is like a certificate of birth or something like that. It is certifying your identity. And how it works is that you need some trusted authorities here, like a CA and a CA, which is assumed to be trusted, to actually provide the certificate for you. So we'll talk about what a certificate is. Um, it is based off of the TLS protocol, which is commonly used to secure transit. So like HTTPS is just HTTP plus TLS, and SMS is secured by TLS as well. Something good that comes out of TLS is that you can actually make certificates with it. So TLS provides security via certificates, and a certificate is used to associate a public key to a specific entity. So it's associating a public key to an entity. So how you actually create a certificate is you have your identity, which is called the distinguishing name, which has the format of like CN equals John Smith OU. It is like a name. It can be used for servers. It can be used for websites. But this is just one example format. It doesn't have to be this. But you have the distinguishing name. You have the public key. You have the expiration date, and you have the CA's domain name as well, and you have the CA's signature. So the signature is to say that the certificate authority did indeed look at your request and they've signed it. So this is theirs. So this is how you can verify that the CA actually did take a look at your website before or your server before. So yeah, so this is the CA. This is kind of the organization that we think is responsible for creating the certificates. So they're the only ones that are responsible for creating it. There are some authorities that you can find online. So if you search for the authorities, there's this organization called Sectigo, Let's Encrypt, DigiCert. You can become your own CA if you want, or you can set up like a custom CA that is like only for your private cloud. But like for the public internet, if you want to become your own CA, you can do that. But you have to ask Firefox and Google and all of the sites to add you on the list that we trust. So yeah, so a CA is believed to be the root of trust, right? So if you have a CA that is evil, then you can create false certificates and you can create signed malware. So this is a problem with an evil certificates, and this is what motivates something called a root CA. A root CA is established and it's only on for like 1 hour every single year, and it creates the certificates for the CAs. And like after that's done, the root CA shuts down. So you want something that provides the certificates for all of the CAs, and then after that's done, then you have this root CA that you trust. If somebody takes advantage of the root CA, then the world ends. But that's why the root CA is only on for like 1 hour every 15 years to create those certificates. After the certificates expire, then it's turned back on. But until it doesn't, then we're fine. So yeah, so registration authority is being used as like an intermediary between a CA and a PKI. So the CA produces these certificates, the RA handles everything around that. So if you actually want a certificate, you ask for a CSR, a certificate signing request. And how that looks like, we're going to go into it later on, but you would package a little bit of information about yourself, and then the RA would actually verify that it wasn't actually taken before, and it would forward it to the CA so that the CA can sign it. And you're also responsible for a certificate revocation list, which is like a blacklist of certifications. So the CSR is the thing that the subject wants to request. So they want to request a certificate. What it actually looks like is it is the owner's identification, it is the owner's public key, and also the owner's signature. So you want to ensure that this is actually coming from the owner. So you want a signature to say that this indeed did come from me, because you can verify from my public key this indeed did come from me. So this is what the CSR is going to look like. You can add more information depending on the CA provider that you need, but this is like the fundamental bare bones structure. And how you create it is obviously you combine the stuff in the CSR, and you add an expiration date and the signature of the CA. So that this is what the CA will actually do to create the certificate. Yeah. So now that you have a certificate, how does someone validate that you actually are what you say you are, right? How do we know that you don't have an expired certificate, or like the certificate is actually yours? Well, what you do is you have to send like the person that's going to communicate with you. They're going to send a certificate to a validation authority, and the VA doesn't actually have to be something like an actual organization. It can be something in your browser. Um, it's supposed to provide the validation essentially. So there are different ways that you can implement a VA. You're going to use a combination of these, but you have to use something called a certificate chain of trust. So in the certificate, obviously you can see the CA that signed it. So you look at the CA that signed it, and you check their certificates, and you check who signed that CA's certificate, and you go on and on and on until you get to the root CA. You also have the certificate revocation list, which is like the blacklist of all of the certificates that have been expired and revoked. And then you have the OCSP, which is something in your browser that will monitor which certificates are fine. It's kind of, I guess it's kind of like a cache of the CRL. But yeah, so I think that's it for everything we needed to talk about. That's actually pretty much it. So there is a lot more cryptography, a lot of cool stuff. If you're interested, maybe we'll do some more talks on later on. There is a lot of cool stuff happening in the blockchain world, especially with zero knowledge proofs, which are kind of games that you play to show that you know something without actually showing that you know it. So like you know a secret, but you don't want to show anybody that you actually know the secrets, because that secret is, well, to be secured. So you want to show that you know something without actually sending it over. There's post-quantum cryptography, which is very relevant right now because a lot of quantum systems are being developed, and they're different. Well, it's a fast-moving field, and commercial quantum equipment, when it comes out, can break a lot of asymmetric cryptography with the Shor's algorithm, and can reduce the time complexity of a lot of things. with the Grover algorithm. And there's also lattice-based cryptography, which is kind of useful if you want to do something called homomorphic encryption. But that is pretty much all that we have to talk about. There is some resources here if you're interested. There's some courses. There's also the war game Crypto Hack, which is very good. But yeah, that's everything we have to talk about today. So we're gonna stay for maybe 10 minutes